DuoTouch, passive two-footprint attachments using binary sequences to extend touch interaction. Touch panels are designed for finger input, but they also register touches through conductive materials. This enables locating controls outside the touch panel and combining it with mechanisms that provide tactile feedback for richer input. However, increasing the number of commands requires covering more of the touch panel, increases the physical footprint, and complicates the wiring of the electrodes that users touch. We present DuoTouch, a passive attachment for capacitive touch panels with two contact footprints and two traces. It captures motion as binary sequences and runs on unmodified devices. DuoTouch provides two decoders on the same two-trace architecture, the aligned configuration and the phase-shifted configuration. The aligned configuration maps motion to fixed-length binary sequences for discrete commands. Two traces use a cone-shaped sequence pattern. Sliding a conductive knob bridges teeth to register touch while gaps produce no touch. We encode touches as 1 and gaps as 0, then use codebook matching to map the sequence to a command. The phase-shifted configuration estimates direction and distance from intertrace timing offsets for continuous control. The traces are designed so that both footprints produce periodic touch events during sliding. In this example, left-to-right motion makes the upper footprint lead, right-to-left makes the lower lead, and the number of cycles gives distance. We developed a design support tool that automatically adjusts design parameters and outputs a sequence pattern for the desired interaction type. The system generates CAD-ready fabrication files that users can import into PCB CAD tools for final layout and placement. We also provide an STL library for basic controls. The housing and mechanical parts are 3D printed, and the PCB is mounted to complete the device. Aligned configuration application, a touchpad attachment with 8 sliding buttons. The buttons ride over a PCB sequence pattern and record a binary sequence when pressed. Each sequence is unique, so each button maps to a different shortcut. With only 2 contact footprints, it preserves the pointing surface and supports simultaneous pointing with direct finger touch. By introducing a bidirectional pattern, a single switch can encode 2 commands, such as pull up to copy and pull down to paste. Phase-shifted configuration application, a dial attachment with a periodic pattern around the circumference, integrated into a phone ring holder case. Rotating the dial controls continuous input. Hybrid application, rails carry a sequence pattern on top for the aligned configuration and a periodic pattern on the bottom for the phase-shifted configuration. Pulling the strap triggers code recognition and switches to one-handed mode, moving the shutter button to the right side. Sliding on the lower periodic pattern then adjusts camera zoom. To identify sequence pattern parameters for reliable recognition, we varied electrode width with spacing set relative to each width and tested a range of manipulation speeds. Across both devices and decoders, accuracy decreased as input speed increased, with a stronger decline for narrower electrodes and at lower sampling rates. Within the sampling limited bound, accuracy remained high across conditions. We conducted an exploratory study to gather initial impressions of 3 application prototypes, to elicit application ideas for everyday use, and to surface potential concerns. UEQS results indicated a positive user experience across pragmatic and hedonic dimensions. Participants were receptive to adding input to familiar accessories. Participants proposed diverse scenes, many for media control, and envisioned uses that combine physical interaction and sensing. They also highlighted ease of use, tactile feedback, and expressiveness, concerns centered on size and weight. In summary, these are the key points of DuoTouch.